So I'd like to welcome Matt Huber from South Africa, who's applied to join us, and he'll be talking about impact processes. And Matt, I'll turn it over to you now.
All right. Yeah, thank you for inviting me to speak to you. I'm going to be talking about the Vredefort impact structure in South Africa, where I've been working for the last few years. So before I get going, I want to just quickly run through a little bit of my background. I grew up in the United States, studied at the University of Tennessee for my undergrad and Louisiana State University for my master's degree. Then for my doctorate, I went across the pond to the University of Vienna and studied, that's where I actually began studying terrestrial impact craters directly. And then I did a postdoc at the Free University of Brussels before moving to South Africa, where I first worked at the University of the Free State in Bloemfontein, and now I work at the University of the Western Cape in Cape Town. Throughout all of my travels and adventures, I've had lots of people that I've worked with that have contributed mightily to everything that I'm going to be showing you. And so before I go any further, I just wanted to thank my many co-authors, especially Elizabeth Kovaleva, Christian Corbel, Francois Faure, and Martin Clark, who have been especially close collaborators. So I'm going to be talking to you about impact craters on Earth, which are a little bit different than impact structures on other planets because they're not so well exposed. There's about 200 impact structures on Earth, and of those, only 3 come up to what we might consider basin-sized impacts, which would be the Sudbury structure in Canada, the Chicxulub structure in Mexico, and the Vredefort structure in South Africa, with each of them being between about 200 and 300 kilometers in their original diameter. When we talk about basin-sized impact structures, most of what we know comes from looking at other planetary bodies, such as impact craters on the Moon. This is Schrödinger crater, where we can clearly see an outer rim, an inner peak ring, and a melt sheet. This is what I'm going to be referring to in this talk. This is probably approximately what Chicxulub, Vredefort, and Sudbury looked like when they were fresh impact structures on Earth. And so this type of impact structure has melt ponding inside and outside of the peak ring structure and a heavily fractured crust below the melt sheet. This type of crater forms from massive impact events. These craters all formed from impactors that were likely larger than 10 kilometers in diameter at the time that they hit. So I'm going to show you an ISAIL animation, a numerical model of a crater forming. So this is the impactor, about 14 kilometers diameter. This blue box is the same as this blue box, and this impact is going to be moving vertically. Of course, we're in half space here. If I can start it. Why does it not want to start? Apologies. It did go before. There we go. So we can see when the impact happens, it immediately opens a transient cavity that goes down to 30 kilometers depth and then rebounds to above 10 kilometers above the pre-impact surface before settling down. In the process, this overturns the crustal material, giving you an overturned limb, and results in massive uplift of the central material. So we can see even materials that started 20 kilometers below the pre-impact surface wind up at the exposed surface. In the case of Vredefort, we have further cut down into this structure by eroding away a lot of the uppermost material, and that's what we can actually see at the surface. We have this basement material that's brought up significantly and the overturned supercrustal rocks. We know that when a large impact of this type occurs, we have a zone of vaporization and melting of the target rocks, and then as the shock wave expands, this goes into a zone of shock metamorphism and then fracturing and brecciation. This results in the formation of a lot of different impactites or shocked products, and we're going to be looking at a few of those that are relevant in understanding what happened at Vredefort. So if we take a cross-section of the structure, it would have looked something like this. The target rocks were granites of Archean age. These are very old granites and granitoids. And then sitting on top of that, there was a supercrustal sequence of volcanic and sedimentary rocks. Now, because Vredefort is a very old impact structure, it's experienced a lot of erosion. So a lot of the uppermost features of the impact structure have been eroded away. So that now what we're looking at is a lot of the material that's at a significant depth below the original impact crater surface, which gives us a unique window into understanding what's going on at depth below one of these large impact structures. In the map view, you can get a sense of what's going on with Vredefort. Now, in this particular map, I've drawn a circle representing 300 kilometers diameter. So that would have been about the size of the impact structure immediately after it formed. Not so much is visible at that distance in the modern day geology of South Africa. It's either been eroded away or overprinted by other structures. In the subsurface, there's still significant damage to the rocks out to the distance of 300 kilometers, but not easily represented in this type of map. Most of the direct evidence of the impact comes from the inner part of the impact structure. This is the so-called Vredefort dome, because it is a topographic uplift, so it's a dome. And we can see this curved band of rocks. This probably represents the roots of the peak ring structure of the impact when it formed. And that's where we're going to zoom in and look at a lot of interesting materials. Now, when I say that the middle part of the structure was uplifted, that's quite significant. What you're looking at is a 3D seismic reconstruction of what the granites look like in the subsurface. So because of the significant number of mines in the region, there's been a significant amount of seismic surveys of the area. So they've been able to completely reconstruct what the various lithologies look like in the subsurface. This is the uplifted granitic material, and the Vredefort dome is really a transect across this uplifted granitic dome. If we overlay the sediments of the Witwatersrand supergroup on top of that, which we'll talk about a little bit later, we can see how these supercrustal rocks are draped on top of this granitic basement and also were significantly uplifted by the impact. As I said, a lot of the damage that was created by the impact is really only visible in the subsurface. So the center of the impact in this image is really on the right-hand side of this interpreted seismic profile, but we can see the edge of the granitic rocks, the beginning of the supercrustal sequence, and the significant amount of faulting that extends out all the way to that interpreted diameter of about 150 kilometers from the center, or 300 kilometers diameter total. So this is where the size of Vredefort is based on. We have a pretty good resolution on the age of Vredefort as well. It occurred 2,020 million years ago. This has been studied for quite some time now, and a real consensus about the age was reached in the 1990s when it was possible to identify zircons that crystallized from granites that actually formed as a result of the impact. So this is a very robust age of 2,020 million years, probably more precise than most of the impact craters that we know on Earth. Now, if you want to actually understand Vredefort, you need to go to Vredefort, and if you go to the small town of Vredefort on just the right day, you can enter a lucky draw and win a sheep. But if you're not interested in sheep, you're probably going to look at the impactites. And in terms of things that are visible with the naked eye, the impactites really fall into three categories. First, there's shatter cones, which are ubiquitous throughout the structure, and I'm not going to be discussing those in this talk. And then there are two different types of impact melt, and those are the Pseudotachylites and the Vredefort Granophyre. These are both impact melts, and they superficially look similar to each other. They're both dark-colored, almost nondescript rocks, this black coloration or dark brown. The difference between them is that Pseudotachylites are melt that formed basically where you find it. So this is melt derived from the immediately surrounding granites, whereas the Granophyre is melt that derived from the melt sheet and moved down to be emplaced at the current erosional level. We'll be talking about how that happened in a bit. Now, with both of those, shocked minerals and high-pressure polymorphs are present inside of the rocks that help us to understand their role in the impact, and we'll touch on those as we go. So we'll start by talking a bit about pseudotachylites. Now, pseudotachylites are found in many places throughout the Vredefort structure, but one of the better-known localities is the Loikop Quarry, which is what you're looking at now. Loikop means lion's head. This was mined for dimension stone for many years, and you can see this yellow to pink granite has these black lines that cut through it and go all the way up through these hills. Those are massive pseudotachylites developed in the granite. So when we zoom in on that, we can see these thick pseudotachylites, this black material, and you can see that it's loaded with these inclusions of granite that have fallen from the wall rock and migrated through the melt down into these thick melt veins. We've looked at the orientation of a lot of these blocks, and we can see that they have rotated and somewhat had some degree of migration from the host granite, but it is very similar composition to the host, so very little movement. In many cases, when we look at pseudotachylites in detail, this is a smaller scale pseudotachyllite, we can get a strong sense of the movement that occurred within the rocks. So here we have the pink granite, and we have this black pseudotachyllite, and you can see inside of this vein that a lot of shearing has taken place, which gives us a strong indication that there was a sense of movement along a fault, and that the pseudotachyllite was melting in this high amount of friction that was taking place. We can also see areas like this where we have a fracture that is parallel to the plane of movement, and then we have lensing open of this block where the melt is moved into this space. So we have movement in the same direction, but a little extension taking place. So we can learn a lot by studying pseudotachylites. Now, I would emphasize these are impact-generated pseudotachylites. There are also tectonically generated pseudotachylites that are often known colloquially as fossil earthquakes, because the force of an earthquake is enough to generate a very similar type of structure. One interesting example that we found where this becomes really important, this is a granite where we can see two different pseudotachylites cutting through this particular granitic block. But when we looked closely, we saw that the second vein was actually cutting through the first vein. So we made a microscope slide of this, and we could very clearly see that the first vein has been recrystallized and experienced a long history. It looks very different than the second vein. So it became clear that this was a case where there was an impact-generated or a shock-generated pseudotachyllite that was cross-cutting and offsetting a tectonically generated pseudotachyllite. So this is something that had occurred to these granites long before the impact that was then affected by the impact. This gave us an opportunity to try to understand how the deformation processes going on in these pseudotachylites can differ between the tectonic and impact regimes. And the way we did that was by looking at microstructures within shocked zircons. So if you're not used to looking at electron backscatter diffraction maps, what you need to understand, each one of these represents one crystal of zircon, and the colors represent the degree that the crystal lattice is bent compared to a reference point, where the star is the reference point. So we took zircon first from the host rock, and what we see, and this is zircon from the host rock, it's very colorful, but that's because there's not very much going on. It's only bending to about 5 degrees, which is not very much. So in the host rock, the zircons came out mostly unscathed. We then took a zircon from the tectonic pseudotachylyte, and we can see the scale on this goes up to 25 degrees. This is a significantly more deformed zircon, and especially there's this planar deformation band that concentrated this bending. That's also been recognized in places like the Alps, where there's significant tectonic pseudotachylites that are developed. Then we looked at the impact-generated pseudotachylyte, and there we saw that the bending of the crystal lattice of the zircon was up to 90 degrees. This is a zircon that got completely folded in half by the force of the pseudotachylyte. So by the generation process of the pseudotachylyte. So this gives us a very clear way to distinguish the tectonic pseudotachylites from the impact pseudotachylites by examining the microstructures in zircon very carefully. Now, all of the pseudotachylites that I showed so far are developed in granite. There's other rock types in these basement rocks as well, and especially dolerite. Now, in fact, in the Vredefort structure, pseudotachylites, these sort of in situ melt veins, they're formed in every type of lithology that there is. But when we started looking at the dolerites in particular, we saw something that caught our attention. Now, first of all, the pseudotachylites are a little bit hard to spot because it's a dark-colored rock with a dark-colored vein cutting through it. And then we started noticing that there were some unusual inclusions inside of these. So we found one particular sample, and we cut into it, and we saw this nice pink granite sitting in the middle of this dolerite. Now, as I said before, what's really the defining feature of pseudotachylites is that they are melt that is entirely local in origin, that has not traveled a long distance. In this case, there was a granite adjacent to the dolerite, and what we see when we make a chemical map of this melt is that we have the host dolerite, we have a melt that is very similar in composition to the dolerite, and then we have another melt that is a mixed composition between dolerite and granite. Then we have this large granite clast that is included in the middle of this dolerite pseudotachylyte. So this has to represent a case where there was a granite adjacent to the dolerite, where the granite fragments were injected into the dolerite during the impact process and then frozen in this position. This is probably only a movement of between 10 and 20 meters distance. So it's not an especially long distance, but it still is showing that there was transport of this molten material during the impact process. So moving on from pseudotachylites, I'll now talk about the other melt rock in Vredefort, which is somewhat more complicated to understand. Now, the Granophyre dikes are present in a series of dikes on this map represented by these black lines. There are Granophyre dikes that are in the middle of the Vredefort dome. These are called the core Granophyre dikes that are in the core of the Vredefort structure, and then the others are along the boundary between the core and the collar rocks, or the core-collar boundary. And these are a little bit different from each other. So we'll start by looking at some of the Granophyre dikes in the core of the structure. Now, to understand what these represent, it's helpful again to look at the moon. So this is an impact structure where there's a melt sheet that has these very clear fractures that obviously developed after the melt sheet was crystallized, or at least partially crystallized. This has to represent some kind of late stage process that's occurring in the life of the impact structure. Now, there's different ideas about how these form. One of the ideas is that as the crust is relaxing and uplifting after the impact process is completed, it allows for fractures to open so that the melt drains from the base of the melt sheet, which forms these fractures at the top. This is sort of the model that we've adopted for understanding the Granophyre dikes. So again, we had this melt sheet that was at the surface of the impact structure, and then the Granophyre dikes poured down into the crust below the impact structure. Then the melt sheet was eroded away, and the Granophyre dikes are what we have left over. When we go out in the field, this is sort of what they look like. This is the Daskop Granophyre dike. This is the first one that we started studying and that we have a pretty good understanding of now. You can sort of see that this is more or less a chain of boulders is what it looks like. These are these brown rocks sticking out above the ground. If we were to clear out the grass around here, we would see that this is all granites on both sides of this dike. And if you were to walk along this dike and look at it carefully, you might notice these carvings, this artwork carved into the dike. These were carved by the San people, who were a nomadic people of southern Africa that carved these as much as 3,000 years ago. The archaeologists have given us different numbers, but about 3,000 years is the age. Now, looking at these, you can also notice there's a lot of inclusions inside of this rock. So the rock itself, it's a fairly homogeneous material, and then there are a lot of these inclusions of rock fragments. Those are rock fragments that were picked up by the melt as it was descending from the melt sheet. And as we started to walk up and down this dike and look at it carefully, we realized that these were not evenly distributed throughout the dike. Now, there's a lot of different types of these inclusions, and you can see examples like this one where this was obviously an elongate clast that as it was being mobilized by the impact melt, it was heated, began to plastically deform and spun on itself so that now it's wound up into this shape. We also see these types of clasts where they've been heated and plastically deformed and folded in half. And we see some areas where there's really large numbers of these fragments in close proximity to one another. So what we did was we went boulder by boulder and made an estimation of the percentage of the boulder that was covered by these clasts. And we were able to generate this map. So we mapped out every one of the boulders. We looked at the percentage of the clasts in each boulder, and what we realized is that there was a much higher concentration of these clasts on the southern margin of the dike. So in these areas, the total percentage of the clasts in some areas could get up to close to 50%, whereas on the opposite side of the dike, there would be many areas that were almost free of any lithic materials inside of them. So there was significant heterogeneity in terms of the class distribution, but it was not random. Now, in the process of looking at it this closely, we also recognized that there were these elongate structures that were coarse crystalline. So when we looked at them under the microscope, we could see that there were these much larger crystals inside of these veins than in the host rock. And after looking at these, we surmised that these are very likely areas where fluids in the melt would be escaping along these veins. So these are elf. We then went on to another one of the core Granophyre dikes. So we were at the Daskop dike. This is now the Lesotho Crawl Granophyre dike, which is one that we've now studied quite a lot because it has this excellent pavement, which is a coherent block of material that is fully preserved. It's about 5 meters wide, and we are very fortunate at this site because we have the contact with the host granite on both sides of the dike. So we can physically put our finger on the contact on either side of the dike. So we're sure that we're looking at the entire width of the material that's here. It's not that something's eroded away and giving us a false impression. So in this case, we used a drone to create an orthophoto of the dike. That's what we're looking at here. And then my postdoc went and in GIS, he circled 2,000 different inclusions, which we're pretty sure covers the entire dike, and mapped out exactly where they are. And what we can see in this case with the distribution is, again, it is very inhomogeneous, but not at all random. In this case, the clasts are all on the northern margin of the dike, very heavily concentrated, whereas on the opposite side of the dike, as well as in the middle of the dike, there's almost no inclusions that are present. So after doing some modeling on this, we came to the conclusion that what's most likely happening is that the melt rocks that pick up fragments as it's traveling cool down somewhat compared to the melt that does not pick up any fragments. This makes the fragment-rich melt and the fragment-poor melt behave as two immiscible liquids. So as they're flowing down the dike, the immiscible liquids separate into two different sections, with the clast-free melt or the clast-poor melt traveling down the center of the pipe, essentially, and pushing the clast-rich melt to the edges, where it is then crystallizing and cooling. So we learned a lot about the flow properties of the melt by studying the inclusions, but then we wanted to know what was going on with the dikes at depth. So then my good friend Francois Fourie, he is a geophysicist, and he brought out his nice equipment, these big stakes. We hammered those into the ground in a nice transect across the dike. And the idea was that this would give us a picture of the resistivity of the different materials. So the granite would have a certain resistivity, and the Granophyre would have a different resistivity, and we would be able to see how far below the surface these extend. We were a little bit surprised by the results. In these images, this is showing the profile that we took. All of this material in green and blue is the granite. The material in red is the Granophyre. So this is a depth of about 3 meters below the surface that the Granophyre disappears, that it's no longer present in the subsurface. We expected these to go down basically forever. Because these dikes are made of material that derived from the melt sheet, and we've had 10 kilometers of erosion, that means that this melt rock survived 10,000 meters of transport, but if we had had 10,003 meters of erosion, then they would be gone. Numbers are estimates there, but it's really an incredible coincidence that anything of this material is preserved. So we studied the core dikes after quite extensively, and then we moved on to the collar dikes, and especially the Koppies Kraal dike, this long dike in the middle of the core collar boundary. And there's some rather significant differences between the core dikes and the core collar dikes. The biggest difference is that in the core collar, there is a second type of Granophyre. So all of the core dikes have the same exact chemistry, the same composition, the same petrography, everything about them basically is the same. In the collar, we see the second phase of Granophyre start to show up. When we take the resistivity survey of these collar dikes, it's on a bit of a slope, that's why this is tilted, but we see that the dike material extends as far down as we can measure. all of the core dikes that we've looked at, they all disappear below 5 meters depth. We thought that this might be an instrumental error, so we went out with shovels at one point and dug down, and sure enough, after a couple of meters, these things disappear. So the core dikes are very shallow. The collar dikes are wider. They extend further down, and there's another composition that's present. When we look at the chemistry of these, where we have the Granophyre A and Granophyre B with a sharp contact between them at many different locations that we've identified now, what we see is that all of the core dikes and all of the Granophyre A that we find in the collar all have exactly the same composition, or compositional range. They're all dacitic in composition. When we look at the Granophyre B, we see that it's much more mafic. These are andesitic in composition, and it's actually much more similar to the melt rocks that we find at the Sudbury impact structure than what we find at Vredefort. So this is a really different material. Now at Sudbury, these similar types of dikes, the offset dikes at Sudbury, those are mined as one of the largest nickel copper PGE deposits in the world. So when we started looking carefully at the B phase, which really wasn't recognized until just a few years ago, we identified these brown nodules, and this made me a bit excited because they're brown in color because they're rich in sulfides. These types of sulfide nodules are exactly the sort of thing at Sudbury that carries the metals. So we made some microscope slides and looked at them, and sure enough, we found that there's significant nickel, copper, and platinum group elements inside of these nodules. Now, unfortunately, these are extremely small nodules. This is not an economic deposit. This is not the next great resource, but it probably represents the erosional remnant left over from some kind of large metal deposit that existed in the past. If the erosional level was a little bit less, we might have a really large PGE deposit also at Vredefort. Now, between the Granophyre A and the Granophyre B, there are also some significant textural differences. So these, the Granophyre, they're all made of a relatively narrow range of minerals. We have feldspars, we have pyroxenes, we have biotite, and we have quartz. And those are about the only minerals. In this case, this is the Granophyre A, and we can see this long pyroxene crystal that has been bent. And this is very interesting because what that shows us is that as the melt was cooling down and crystallizing, the pyroxene needle crystallized, but the melt was still mobile. And so as it moved, it bent this crystal into this shape. Then later, the rest of the material crystallized. So there had to be some kind of motion going on still while the Granophyre A was crystallizing. We can contrast that with the Granophyre B needles in the Granophyre B, but what we do find are big clusters. These again are pyroxenes. These are not pyroxene needles. These are large crystals of pyroxene that are interlocked with one another, making these mafic clusters. So we see very different styles of crystallization in both of these. In this case, to form these clusters, the melt needed to cool down at a very slow rate. To make needles of pyroxene needs to cool down at a very fast rate. So there's significant differences in the cooling history as well as the chemical composition of these two different phases of the Granophyre. In order to sort of get a handle on the temperatures that we would need to be looking at, I did some modeling using melts based on a number of different compositions that the initial Vredefort melt sheet might have been. Now, when you have an impact of this scale, it has the convenient aspect that it melts the entire upper crust. So you can essentially use the melt sheet, the average composition of the melt sheet of a large impact like this, as an estimation of average crustal composition, and you can use average crustal composition to estimate the melt sheet composition. So I used a few different estimations of the melt sheet and also some estimations of the Sudbury melt sheet to get a feel for what the initial composition could have been, and then I allowed that to crystallize as it cooled off. Most of the material remains liquid until about 1150 degrees centigrade, and then almost everything is crystallized by about 1000 degrees. So that gives us a fairly narrow temperature range in which crystallization could have taken place. Now, I also decided to look at the rate of cooling of these dikes, and we have some constraints on this. Now, we can get an estimate of the maximum temperature that the melt could possibly have been by looking at minerals like bedelite that start to disaggregate at about 2,300 degrees Celsius. And there's some evidence of that, but it was not clear if those types of temperatures were representative of the whole melt sheet or the whole melt body, or if that was just a localized, extremely high temperature area. When we look at the rocks themselves, we see that there are these cooling joints, and those cooling joints can only be forming once there's some degree of undercooling taking place. Moreover, we can look at the host rocks around these dikes, and we can see that those are mostly not melted. So if we try intruding the melt at 2000 degrees, and we model that, we see that there's a significant amount of the host rock that goes above its melting point and would have been melted. However, if we try at a lower temperature of intrusion, then we see that the dikes would cool off significantly faster and that the host rock would not be so strongly affected, which is much closer to what we see in the field. So we probably have both the temperature range of crystallization and the amount of time that it took for these dikes to cool off. So we've learned quite a lot about the emplacement history of the dikes, and we can basically put together a model of what this emplacement would have looked like. And it probably took place over the course of about 10,000 years after the impact happened. So we know that all of the core dikes and the A phase of the core collar dikes all have the same composition. So those are probably derived from a homogenized melt sheet within less than 1,000 years after the impact occurred, because that's about how long it would take for differentiation of the melt sheet to occur. Then, after differentiation of the melt sheet occurred, there was extraction of the B phase of the Granophyre. This more mafic composition was brought down at a later stage. That would have to happen after about 10,000 years. So this gives us a sort of multi-phase emplacement model of how the Granophyre dikes developed. Now, with the last couple of minutes, I'll just talk about some of the larger implications of the Vredefort impact. Now, the impact occurred at about 2 billion years ago, and by that time there were already a lot of significant things that had happened on the Capfall Craton. The Capfall Craton preserves a rock 6 billion years old. And so there's a lot of geological history when Vredefort impacted. So if we look at the Capfall Craton, we can see Vredefort is right in the middle of that. And we can see that it hit right in the middle of this big brown material here. This is the Witwatersrand supergroup. Now, the Witwatersrand supergroup is really significant globally because it has produced about 1/3 of the gold that's ever been mined by humanity. We can see the mines themselves are in this blue color in a semicircle around the Vredefort structure, with Vredefort being a bullseye right in the middle of these gold fields. This is not a coincidence. So this gold was discovered in the late 1800s and exploited by South Africa over the last 150 years or so, so that South Africa has been one of the top producers of gold. Now, this gold, almost all of it, comes out of the Witwatersrand Basin. So what you're seeing with this massive amount of gold, that's just the Vredefort associated gold. The material itself looks like this. You have this, these are sedimentary rocks. That's these formed in basically rivers. As mountains were eroding, these pebbles were eroding down them, and all of this golden material, that's pyrite, but the gold is hosted by the pyrite. So there's significant gold inside of these rocks, and there's also significant debate about how the gold got there. There's one camp that believes the gold was already present in the rocks when they formed. There's another camp that believes that the gold came in hydrothermally as a later process. But to simplify the debate, both sides have a good point. Some of the gold was already there when the rocks formed, and some was brought in hydrothermally. And it's very likely that the Vredefort event was a significant part of the hydrothermal history of these deposits. Now, definitely, when the impact occurred, it lifted up these rocks of the Witwatersrand. They would have been too deeply buried to mine or even discover if Vredefort hadn't occurred. But Vredefort also generated modeling shows that there would have been temperatures in the middle of the structure high enough to actually melt the target rocks after the impact. It would have kept the granites at their melting point for quite some time. But the hydrothermal system would have extended out for a very considerable distance, and probably at temperatures high enough to mobilize gold out to the distance where the gold mining has taken place. We know that the hydrothermal system around these large impacts is driven by a lot of different processes. Part of it is that these deeply buried rocks are lifted up. The mantle itself is partially lifted up, so the heat profile from below is increased. The melt sheet also provides a heat source from above, and the large number of fractures that have moved also are generating heat. There's many different sources of heat around these large impact structures that can be circulating fluids even at significant depths. Now, one way we know that the hydrothermal system of Vredefort had to affect the Witwatersrand is that all of the micas that have been argon dated within these gold deposits, even though the host rock is about 2.8 billion years old, they all give ages of the Vredefort event itself. So there was a resetting of the micas by the impact. And there's been extensive studies on the fluids that mobilized the gold in the Witwatersrand, and it is at minimum plausible that the Vredefort hydrothermal system was mobilizing significant amounts of gold. So there's one more aspect of Vredefort I'll finish up with, and that is the material that was blasted out by the impact. So that is the ejecta. Now, the earliest discoveries of the ejecta from Vredefort found there are some spherules in Greenland and in Karelia in Russia that are indistinguishable in age from Vredefort and that have platinum group element signatures similar to the Granophyre itself. So it is likely that these are distal ejecta from Vredefort. But we know Vredefort impacted in the middle of the Cap-Fault craton, and so if we look out for more proximal ejecta, even though significant erosion has happened at the Vredefort structure itself, it's likely that areas around the Cap-Fault craton preserve ejecta from the event. So I've highlighted a band of rocks in purple here that has an age. These are sedimentary rocks that have an age indistinguishable from Vredefort that my team has been looking at in the last couple of years. And these are three sites in particular where there are mining operations, where iron is being mined, where there are breccias that we investigated to see if they could be Vredefort related. What we found at the top of the pile of breccia is accretionary lapilli. These are very often found associated with volcanic deposits, but they're also associated with ejected deposits from large impacts. We found these polymixed breccias made of many different lithologies shoved together. We had very nice access to drill core because the mines were very friendly in giving us access. And we found big piles of mixed up types of rock that were jumbled together and didn't have a plausible explanation for how they formed in a subaerial environment. When we started looking at these more carefully, we found that they were loaded with shocked quartz grains. And there were tons of planar deformation features and planar fractures. And especially, this case was interesting because we saw that these were planar fractures in a quartz grain that were then infilled with hematite, suggesting that the iron that was being mined was actually coming in after the ejecta had been deposited, that it was coming in by a later process, and the ejecta itself was actually acting as a substrate that was especially effective at absorbing these iron-rich fluids. So we had a thought, would it be possible to take an ejecta deposit and alter it to iron? In order to test this, we took an accretionary lapillus. This one is from the Chicxulub impact, the one that killed the dinosaurs. So this is a known ejected deposit that's much younger than Vredefort. We had a look at it with a scanning electron microscope and a microprobe to make sure of what it was composed of. We then stuck it into an autoclave with some fragments of hematite to see what would happen to it. And sure enough, we saw that this material was altered to iron-rich minerals. So this type of replacement reaction absolutely could happen in the conditions that these rocks would have experienced after the impact. So I'll conclude there. The Vredefort impact, it's the largest impact structure preserved on Earth, and it provides a unique deep transect through this type of very large impact structure. We can especially learn a lot about the impact by studying the Pseudotachylytes and by studying the Granophyre, which reveal a lot about how the impact structure formed and how it evolved after the cratering process was completed. This is a globally significant impact structure because it is associated with the largest gold deposit in the world, and the ejecta is associated with one of the largest iron mining districts in the world. That's where I'll stop. Thank you.
Great, thank you very much. Interesting stuff. I didn't realize so much gold was that's pretty amazing. Anybody have any questions for Matt? I have one question for you that, when you were talking about like bending zircon 90 degrees, I don't know if at the temperatures zircon can be plastic, or if you're able to say determine not just a temperature but a pressure, and to what extent that maybe reinforces the models of the impact ejecta, that are they consistent with that much force and temperature? In other words, is there a way of constraining your models by looking at all this stuff that's happening?
Yeah, I could have made an entire talk about zircon and what we can learn from zircon. It's an incredible mineral, and it's proven really incredible at preserving the various stages of the impact process. So zircon under extremely high pressure converts to reedite, which is you need something like 30 gigapascals of pressure to make that phase transition. But then you can also offset the crystal lattice in various ways that can occur at lower shock pressures like 20 gigapascals. This type of bending of the crystal lattice, if you had looked at the literature 15 years ago, you basically would have walked away convinced that it was impossible. And it's really recent studies in the last 10 to 15 years that have shown that in the tectonic settings, you can get this mild bending of the crystal lattice just in earthquake conditions.
Hmm.
These planar deformation bands, they give you 5 to 10 degrees of bending reliably, even in places like the Ivrea zone in the Alps. These more massive um, uh, shock bands that can form in these deformed zircons. I'm not even sure off the top of my head what pressure is required for those. Um, and one of the troubles with trying to assign the numbers to it, the numbers are really nice and they're really easy to talk about. Um, there's a lot of details in where those numbers come from. In a lot of cases, what's going on is that they will put a crystal into an anvil and slowly increase the pressure so that they can very carefully control the pressure that the crystal is experiencing. But then that is a static pressure, which is somewhat different than a shock pressure. So all of the phase diagrams are based on this type of static pressure experimentation. When they're shock experiments, they can reproduce a lot of the things that we see in nature, but it's much harder to then extrapolate what was the actual pressure that this exact spot experienced. Um, and then, yeah, I don't know that I want to go on about zircons too long here.
Yeah, no, it's interesting to hear about how you people try to put all this stuff together into a consistent story between, models, which are simplistic at some level, and then the real world, which is like not so simplistic. Vicky.
Yes.
Really wonderful talk, Matt. Thank you very much.
Thank you.
I maybe I misunderstood. So just put me right if not. But I thought you modeled early on with a 10-kilometer diameter bolide. Is that correct? And that seems very small to me. From what I've read, we would expect it to be more on the order of, say, 30 kilometers diameter. So can you comment on that?
Yeah, 10 kilometers is on the small end for Vredefort. And I think that the main model of Vredefort used about a 14 kilometer diameter impactor. There's been more recent models that have used a bit larger. There's been a couple published in the last couple of years that have used, I think, 20 or slightly larger than 20 kilometers diameter. This is always one of those challenging things that we don't know. Kinetic energy is 1/2 mass times velocity squared. So we can roughly constrain the velocity into a range. But when you play with the math, you can generate a 300 kilometer diameter structure from a range of impactor sizes. Somewhere between 10 kilometers and 30 kilometers is probably the right answer. 20 kilometers is probably safe.
Wouldn't that a larger size have more of an impact, pun intended, I guess, not really, but on the volume of melt that is formed and how much of the crust that you form. Obviously, it also depends on, you know, what the density and composition of the bolide are, but it would seem to me, just as you said, you know, it's that energy produced that if you, that we would expect. Is there some way of coming at it from how much melt is generated?
I don't know that I've ever directly thought about that before. Um, what you would definitely be affecting to some extent is the shape of the shockwave. Um, and that may affect the cross-sectional area to some extent. So if you had a smaller impactor at a higher velocity, then you would have more of a point source of the shockwave. Um, so if we look at this map, like this Vredefort dome here, all of this granite, it's about 60 kilometers wide, and especially this inner part that's in dark pink, that actually has all of that has experienced some degree of melting as a result of the impact, just generating very high temperatures. And so if you think about a 20-kilometer diameter impactor, the shock wave would have been basically flat across that whole area. So with a larger impactor, then that area that you would have the expanding shell of the impact, I think would be larger, as opposed to a smaller impactor where um, the initial shape would be a bit smaller, and so you would get more curvature of the shock wave, I suppose. Um, Ultimately, in terms of melting the rocks, a lot of what's going on is shock melting. There's some degree of frictional melting as the rocks are moving past each other. That's some percentage of the pseudotachylites are forming as a result of that. Um, the impact melt itself, the melt sheet, that's forming because you just are exceeding something like 100
Froze up.
structures of the minerals. Sure, the extent to which the shape or the size of the impactor would actually matter if they had the same energy.
Thank you.
I'm not sure.
John.
Yeah, hi. Matt, great talk, really fascinating presentation. And what a really interesting place to study. You did a great job sharing lots of different types of documentation and looking at the different geologic relationships. So it's a lot to digest. My question is not about any of the particulars here, but I'm just thinking very broadly speaking, any thoughts come to mind about comparing Vredefort with the Sudbury structure? They're first order, you know, not that different in age. The target materials are somewhat similar and so on. And I'm just wondering, not being very knowledgeable about either one, if there's any you know, standout either similarities or differences between them that we can learn from in terms of how the impact process on Earth during that sort of general time period may have played out.
Yeah, I think that they're remarkably similar to one another. And oops. Actually doing in a couple of different papers, the reason why this Sudbury field is here. These are the Sudbury offset dikes. The compositions of the Sudbury offset dikes. And we can see that this Granophyre B overlaps entirely with the offset dikes. And my contention is really that these are the same thing, that the bulk melting of the crust in Canada, the bulk melting of the crust in South Africa, it produced melts of the same composition that evolved exactly the same way, that produced exactly the same melt products, that had exactly the same isostatic uplift after the impact, and produced exactly the same dikes. And that's one of the reasons why I got very excited about finding these sulfide nodules in the Granophyre B, because I think that what we're looking at is just different erosional levels. At Sudbury, you've got these nickel copper PG deposits. At Vredefort, I'm guessing it was there, and we're just somewhere down below that now, and it's just eroded away. And I think that I like to believe that, because one of the things that it allows us to do is believe that Sudbury is giving us a certain erosional cross-section of an impact structure, and Vredefort's giving us another. I like to believe that we can use this as just two different layers of basically one impact.
Yeah, very interesting. Great. Thank you very much.
What was it? This took place like 2 billion years ago or so, did you say?
Yes.
Well, how far apart were these things 2 billion years ago, given all the continental drift and stuff like that?
Yeah, continents from 2 billion years ago. And especially localizing the cap Volcraton 2 billion years ago is problematic. There are some reconstructions of a supercontinent. All of the recent reconstructions that I've looked at, they show this nice supercontinent, and then the cap Volcraton is just off by itself somewhere. So I think that there hasn't been much success in merging the superior and cap Volcratons with one another. And the impacts are separated by 170 million years. So it's not like it was a twin impact or anything like that.
Well, thank you very much, Matt. This is a great talk, very interesting.